Hello students, this is chapter 3 in science named Atoms and Molecules. The chapter is totally divided into 3 parts and this is part 1 out of those 3 parts. So let me tell you what we will learn in the first part of the chapter. The first thing is laws of chemical combination. There are 2 laws. The first one is law of conservation of mass and the second is law of constant proportion. Then atom, then symbols of atom of different substances, and then atomic mass. So before starting the chapter, let me tell you something about the timeline of discovery of atoms and molecules. Ancient Indians and Greek philosophers, they have always wondered about the unknown and unseen form of matter. The idea of divisibility of matter was considered long back in India around 500 BC. An Indian philosopher, Maharishi Kanad, he postulated that if we go on dividing matter, we shall get smaller and smaller particles. Ultimately, a time will come when we shall come across the smallest particle beyond which further division will not be possible. And he named these particles Parmanu. Parmanu or Kan. In Hindi, these particles he called Kan or Parmanu, and in English, they are called atom. And Anu is known as molecule and Dravya or Padarth is known as matter. So according to Indian history, it was Maharishi Kanad who first talked about Kan and that is why he was called Maharishi Kanad. At the same time, another Indian philosopher, Pakuda Katyama, he also supported the same thing and said that these particles normally exist and these particles exist in a combined form which gives us various forms of matter. It means परमाणु exist करता है, परमाणु से अणु बनता है और उससे हमको पदार्थ मिलता है. Atoms are there. When atoms are combined, we get molecule and then only a substance or matter is formed. Around the same time, ancient Greek philosopher Democritus and Leucippus, they suggested that if we go on dividing a matter, a stage will come when particles obtained cannot be divided further. Democritus called these individual particles atom. All this was based on the philosophical consideration and not much experimental work was done to validate these ideas. That was totally based on theoretical explanations. And by the end of 18th century, scientists recognized the difference between elements and compounds and naturally became interested in finding out how and why elements combine and what happens when they combine. So it was Antony Lavoisier who laid the foundation of chemical science by establishing 2 important laws of chemical combinations. So in next slides, we will learn these 2 laws of chemical combination. But before that, let us see the history of the atom, the theories and models given by the scientists time to time. At first, in 1803, John Dalton gave atomic theory and solid sphere model of atom. He said atom is like a solid sphere. In 1904, Sir J.J. Thomson gave plum pudding model. According to him, the atom is like pudding and electrons are embedded into it. In 1911, Ernest Rutherford, he gave nuclear model of atom. According to him, there is a nucleus at the center of the atom and electrons are revolving around the nucleus inside the atom. In 1913, Niels Bohr gave planetary model of atom. According to him, there is a nucleus at the center of the atom. Electrons are revolving around the nucleus and they are revolving in some discrete orbits only. And then in 1926, Erwin Schrödinger gave quantum model of the atom. So this was the history of the atom, and these were the scientists who came up with different models of the atom. And one very important and common thing for these scientists is that they all received Nobel Prize for their work, for their contribution in the field of science. Now we will move to your textbook topics. The first one is laws of chemical combination. So let me move to the next slide. Laws of chemical combination. The first law is law of conservation of mass. According to this law, mass can neither be created nor destroyed in a chemical reaction. It means before reaction and after the reaction, the mass remains same. There should not be any change in the mass. Here, this law was given by Lavoisier, and here this is explained with the help of the picture of the experiment. There is the reaction between CaCl2 and Na2SO4, and the reaction occurs. Before the reaction, the mass is 300.23 gram, and after the reaction, the substances are changed. The reaction is CaCl2 plus Na2SO4, but after the reaction, we are having CaSO4 and 2NaCl. This is double displacement reaction that we have already learnt in chapter 1. And we will get the precipitation of CaSO4 in NaCl solution. The nature of reactant and product is totally changed. No matter. But according to this law of conservation of mass, the mass should be same before reaction and after reaction. And it is proved here. The mass of reactant is equal to the mass of the product. So this is law of conservation of mass. What about the second law? The second law says in a chemical substance, the elements are always present in definite proportions by mass. For example, we take a compound such as water. The ratio of the mass of hydrogen to the mass of oxygen is always 1:8. Whatever the source of the water is, this ratio is never going to be changed. Suppose if we take 9 gram of water and it is decomposed, 1 gram of hydrogen and 8 gram of oxygen we will get. And this remains same everywhere in every type of water. So this law of constant proportion given by Joseph Proust, that is why it is known as Proust law also. Now the next problem faced by the scientists was to give appropriate explanation of these two laws. The British chemist John Dalton, he provided the basic theory about the nature of matter. He picked up the idea of divisibility of the matter, which was till then just a philosophy. तब तक किसी ने इस पर वर्क नहीं किया था. And he was the first one who took it, who picked it up and gave his theory. He said, he took the name atom and he said the smallest particle of matter is atom. And according to him, atom is a solid sphere. At that time, this was his model of atom. And he started working on it, and his theory was based on the laws of chemical combinations, and his theory provided an explanation of both the laws. So what was his theory? We will see in next slide. According to his theory, in all the matters, whether it is element, a compound, or a mixture. Everything is composed of small particles, and those small particles are called atoms. He postulated his theory, and according to him, the postulates are: number one, all the matter is made up of very tiny particles, and those tiny particles are called atoms. And these atoms only participate in chemical reactions. Second point, atoms are indivisible particles and that cannot be created or destroyed in a chemical reaction. Third point, atoms of a given element are identical in mass and chemical properties. सेम एलिमेंट के all the atoms will be same. सबकी properties same होंगी. Atoms of different elements have different mass and different chemical properties. Atoms combine in the ratio of small whole numbers to form compounds. Whole number means 2 atoms, 3 atoms, 4 atoms, like that. Half atom will never combine to another atom to form the compound. And then the relative number and kinds of atoms are constant in a given compound. Ratio will never change when a compound is formed. So this was Dalton's atomic theory and the postulates of their theory given by John Dalton. What is an atom? An atom is a small particle, that is the building block of the matter. As you have seen, the building block of the huge building is a small brick. In the same manner, atom is also a building block of the matter. It is very small particle and it is that much small that we cannot see it with naked eyes. We cannot even imagine or compare it because when we cannot see, how to compare? So it is a tiny particle and that is the building block of the matter. How big are atoms? Atoms are very small. Here you can see the picture I have taken from your textbook from page number 33. In this picture clearly it is written that atomic radius of the atom is measured in nanometers. And do you know how much small the nanometer is? 1 nanometer is equal to 1 upon 10 to the power 9 meter. Means 1 meter is equal to 10 to the power 9 nanometer. So nanometer is a very small measurement and atomic radius are measured in this unit. For example, here some atoms are given and their radius is also given. Atom of hydrogen, the radius is 10 to the power minus 10 meter. Radius of molecule of water, 10 to the power minus 9 meter. And the radius of molecule of hemoglobin, 10 to the power minus 8 meter. In the same manner, grain of sand, an ant, and then apple, radius of different things are compared over here and you can see how much small an atom is. When it is so small, how can we measure the diameter and radius of the atom? Before measuring the radius of an atom, let me show you the picture, the magnified image of the surface of the silicon taken by scanning tunneling microscope. It gives you a magnified image of the surface of silicon and you can see the arrangement of the atoms over there. Now radius of the substance, radius of the molecule of the substance. Here you can see these are the molecules of the substance and the distance between two neighboring particles is the diameter, and the half of the diameter is the radius. R is equal to d by 2. So what is d and what is r? R is radius of this atom and d is the distance between two neighboring nuclei, between two neighboring particles. And that distance will be halved, and the half distance will be radius of this single particle. Symbols of atoms of different elements. It was Dalton who was first used the symbol for elements in a very specific sense. When he used a symbol for an element, it means a definite quantity of that element and there is only one atom of that element. The picture I have taken from your textbook, in which you can see the symbols for some elements as proposed by John Dalton. Here hydrogen, phosphorus, copper, gold, carbon, sulfur, lead, platinum, oxygen, iron, silver, and mercury. It was Berzlus who suggested that the symbol of elements be made from one or two letters of the name of the element. And he has derived the name by various means, for example, at first from the name of the place. For example, the name of the copper was taken from Cyprus. At that time, the copper was found in Cyprus, so he has taken the name from there. And for some substances, names are taken from their specific colors also. Gold was taken from the English word meaning yellow. In the modern time, the names and symbols are decided by IUPAC, and every country is supposed to follow the system of IUPAC. IUPAC full form is International Union of Pure and Applied Chemistry. This is the unit that approves names of elements, symbol and units, and they are followed by all the countries in the world. Many of the symbols are the first one or two letters of the element's name in the English. For example, aluminium. The first letter of a symbol is always and always written as a capital letter. This is the rule of writing the symbol of any substance in chemistry. And the second one is always and small letter. See, here you can see aluminium. ALUMINIUM. This is aluminium. And the chemical symbol for aluminium is Al, where A is capital and L is small. If we write it in this form, Al, it means that is wrong. Sometimes the symbol of the substance are taken in a very different manner from the first letter of the name and a letter appearing later in the name. Here two examples are given, chlorine and zinc. C is taken from the first letter of chlorine and L is appearing later. बाद में कहीं appear होता है. तो Cl, that is the symbol of chlorine. In the same manner, zinc, ZINC. Z is the first letter of the name and N is appearing later. The another format is from the name of the element in Latin, German or Greek. Example, the symbol of iron is Fe. Why? Because in Latin, ferrum is called iron. So Fe is taken from FERRUM. So this is the name of iron in Latin language. That is why Fe is taken from there. In the same manner, sodium is taken from natrium. Natrium is the name of sodium. So Na is taken from there. Potassium, chemical symbol of potassium is K, and that is taken from kalium. Each element has a name and a unique chemical symbol. If one chemical symbol is given to any element, that will never and never be allotted to another element. Here you can see the symbols for some elements. The picture I have taken from your textbook, table 3.1, page 34. Aluminium Al, argon Ar, barium Ba, boron B, bromine Br, calcium Ca, carbon C. Here you can see that calcium and carbon both are having Ca and Ca same letters in the starting of the word. So for calcium Ca is taken and for carbon C is taken. Chlorine Cl, cobalt Co, and then so on. Atomic mass. What is atomic mass? Atomic mass is the characteristic of the element, and the unit of atomic mass is AMU, atomic mass unit, or simply it can be denoted by U. What is this atomic mass and how can it be measured? This can be explained easily with the help of an example. Suppose a fruit seller selling fruits and he is not having any standard weight. So what he will do? He will take a watermelon and says this has a mass equal to 12 units. He divides the watermelon into 12 equal parts. So there are totally 12 units, or we can say there are totally 12 fruits. Okay. Now he makes 12 equal pieces of the watermelon and finds the mass of each fruit he is selling relative to the mass of one piece of watermelon. This one piece of watermelon he is using as standard mass. So now he sells his fruits by relative fruit mass unit. Here I can say FMU. Now he is using this fruit unit as a standard mass. So this is FMU. In the same manner, AMU can be explained. For AMU, carbon 12 was chosen as the standard reference for measuring atomic mass. As here the fruit seller has chosen one piece out of the 12 equal pieces of watermelon. In the same manner, carbon 12 isotope is chosen for the standard reference for measuring atomic mass. One atomic mass unit means 1 U or 1 AMU is equal to 1/12 of the mass of the most abundant form of carbon, carbon 12. Let me repeat it. One atomic mass unit is a mass unit equal to exactly 1/12 the mass of an atom of carbon 12. So 1 U or 1 AMU is equal to 1.6606 into 10 to the power minus 27 kg. Very small. Here atomic mass of proton, electron and neutrons are given. Atomic mass of proton is 1.007276 U. Atomic mass of electron is 0.00055 U. You can see that electron is lighter than the proton. And we can even say that its mass is negligible in the comparison of that of proton. Mass of neutron is 1.0086665 U. And here this is given, for example, hydrogen atom mass 1.007825 unit. The relative atomic mass of all the elements have been found with respect to an atom of carbon 12. Means as we have taken 1 unit of watermelon out of these 12 units for standard weight to weight another fruits, in atoms we take carbon 12 as an standard mass, and all other masses are found with respect to the atom of this carbon 12 only. So this was part 1 of atoms and molecules. I hope you understood it well. Now thank you students. We will meet in part 2. By then you keep on reading the chapter so that you can understand the rest of the topics of the chapter. Thank you.